Welcome! This module is about technologies producing bio-based energies and fuel. Although heat and electrical power are very important forms of energy, I will focus on fuel because generating heat and power is state-of-the-art and the technologies do not differ from heat and power produced from fossil resources. In contrast, producing bio-based fuels needs specific technologies which have nothing in common with their fossil-based counterparts. Whereas mineral oil comes from limited areas, is transported through pipelines and tank ships over large distances and refined in industrial centers, biomass has to be produced in a multi-step process. As shown in this list of operations, crop needs to be cultivated and harvested. Biomass is perishable and needs to be prepared for shipping and storage. Mostly only a limited share of the biomass is further processed and ingredients are separated. Therefore, grain is threshed and sugar, starch and oil crop are pressed and extracted. Finally, the resulting purified sugar, starch, oil and residuals are transformed to fuel by thermochemical, physical chemical and biochemical methods. Now let's look on these technologies. The first example I want to show is the production of bioethanol. Bioethanol, important as a transport biofuel, is produced by alcoholic fermentation. The feedstock used is mostly sugar like glucose or fructose. Both sugar contain 6 carbons and are provided by sugar crop and, in the form of starch, by starch crop as shown in the left boxes. Sugar crop, as for example sugar cane, shown here on this photo, is crushed and pressed and sugar is extracted. In the next step, residual sugar left in the biomass is washed out with water as shown here. Now, please have a look on the middle line. If sugar is produced from starch, this polymer needs to be degraded enzymatically by amylases to release glucose. The lower line shows how to produce sugar coming with hemicellulose and cellulose in woody biomass. This is more costly because it needs to degrade the complex and rigid structure of lignocellulose by crushing, milling and pulping, followed by enzymatic saccharification. Lignocellulosic sugars differ from crop sugar because these sugar contain 6 as well as 5 carbons. By nature, most microbes accept only C6 sugar, but can be trained by genetic engineering to accept C5 sugar as well. The next step is converting the sugars by alcoholic fermentation to ethanol. It is mostly performed by yeast. In the fermentation broth, a concentration of 10 to 12% ethanol is reached. Because only yeast tolerate such a high alcohol concentration, the process is biocide by itself and allows to be inoculated by yeast in the robust way shown on this photo I've taken in Brazil. Yeast is separated from the fermentation broth, giving a suspension of high cell density as shown on the left, and transferred to the next batch. Please see on the right photo in the lower left corner the inoculum flowing into the fermenter. After fermentation, ethanol is distilled up to 97% and in another step purified to 99.8%. This bioethanol is ready for sale at the gas station in your hometown. Please keep in mind that ethanol fermentation comes with significant side streams. CO2, slop and vinasse as shown on the right. Slop consists of yeast biomass and solid materials in the broth and goes into biogas plants. Vinasse is the liquid fermentation residue. It is sprayed on farmland as a fertilizer, returning plant nutrients to the field. A third of the sugar carbon is currently emitted as CO2, emitted into the atmosphere. In future, this biogenic CO2 might be valorized as well. Clostridia are bacteria able to use CO2 as a carbon source if hydrogen is provided. Besides CO2, this microbial genus can also transform carbon monoxide into ethanol. Carbon monoxide is the main ingredient of synthesis gas and can be generated from any organic material, This photo documents that the technology works and that companies invest. In Europe, a plant running this technology is currently constructed in Belgium. In summary, according to the state-of-the-art, bioethanol is produced by alcoholic fermentation from sugar and starch crop and some lignocellulosic sugar. In future, CO2 and other side streams along the processing and usage chain can be used as feedstock for bioethanol as well. As mentioned before, bioethanol is suitable for gasoline engines. In addition, it can be used to provide aviation fuel. Several technologies are available. One is the alcohol-to-jet technology, producing hydrocarbons from alcohols like ethanol. The alcohol's oxygen is removed, and the resulting short-chain alkenes are oligomerized and hydrogenated to alkanes, which can fall into the kerosene fraction. Alternative routes to jet fuel start from biomass, synthesis gas, or fatty acids, as shown here in the list. Biodiesel is another well-established fuel. It is produced from vegetable oil by transformation to vegetable oil methyl ester. Like the sugar-derived fuels, it is a multi-step process including cultivation of oil crop, harvesting, storage, oil extraction, and purifying the oil, as you can see on the left of this scheme. According to the state-of-the-art, biodiesel is produced by catalytic transesterification with methanol. Other alkanes, for example kerosene, are generated by catalytic hydrogenation with hydrogen. Biomethane is the next example I like to demonstrate. It is the energy carrier in biogas. This technology is especially useful if highly diverse mixtures of any vegetable and animal material need to be processed. Specific bacterial populations degrade biomass ingredients like polysaccharides, proteins, and fat under anaerobic conditions down to biogas. As shown on this graph, some microbes produce in the first step directly acetate, others convert the feedstock into organic acids and alcohols. Acetogenic bacteria convert these metabolites into acetic acid, CO2, and hydrogen. Next, acetic acid is downgraded by methanogenic bacteria to methane and CO2. Biogas is stored in big gas tanks, as shown here on this photo. Before distributing the gas, it is dried and desulfurized, and as it consists of about 60% methane and 40% CO2, CO2 is separated if necessary. Please note that about 90% of the energy content provided in the feedstock is transferred into methane. Hydrogen is also a kind of biofuel because it is available either from carbohydrates or by splitting water. Both technologies differ fundamentally concerning the energy source. If starting from carbohydrates, the necessary energy comes with the raw material. When splitting water, energy needs to be supplied. Currently, producing hydrogen by steam reforming of fossil carbohydrates is state-of-the-art. But the technology accepts biogas and biomass as well. In a first step, long-chain carbohydrates with the addition of water are degraded at high temperature and under pressure into methane, hydrogen, carbon monoxide, and carbon dioxide. Starting from biomethane is an obvious alternative. In the next step, methane is split catalytically with water into carbon monoxide and hydrogen. Finally, the resulting hydrogen is purified. This method is most common and used in about 90% of the global hydrogen production plants. Please note that the carbon included in the feedstock is emitted into the atmosphere. Splitting water, in contrast, comes without carbon emission. However, external clean energy needs to be supplied. In summary, technologies converting biomass and bio-based materials into biofuel are available, and many are already established on technical scale. However, compared to fossil fuel, processes providing biofuel need many more steps and are therefore more costly. In addition, some methods are energy intensive, thus requiring clean energy input. The good news is that these methods work with very diverse feedstock along the processing cascade, starting from primary biomass down to bio-waste and even CO2 and CO. The future bioeconomy will need such a flexibility when it comes to generating energy.